This lecture is going to talk about a really important metric that we're going to use in model selection, and that is these extra sum of squares and partial sums of squares. Now, before I get into this, I want to emphasize the importance of understanding an ANOVA table. So if you go back to this page from Simple Linear Regression, dealing with simple ANOVA tables, and work through this example in detail. That maintenance cost example is so small that you can really understand all the concepts. The big idea from this is that we want to decompose the variance in our data, all right, in our dependent variable. And that variation in the dependent variable is specified by SST. So this is just saying how much variation, how much total variation is there in the data. Now we're going to decompose that into two pieces. So those two pieces are what the model does and what the model doesn't do. So what the model does we call SSR, the sum of squared regression, sum of squares. What the model doesn't do we call the error sum of squares, or SSE. All right, and these two add up to the total. So with that said, let's go back to this slide. So earlier we've talked about having one predictor variable in the model. Now let's think about having two predictors in the model. So in particular, if we have two predictors, there's three models that we're going to consider. So one is a model that only has x1 in it. The second is a model that only has x2 in it. And the third model is going to have all three variables, both predictors in it. So then the question is, which of these models should we be using? How much benefit do we get by bringing x2 into a model that already has x1 in it, or vice versa? So to answer these questions, I need to introduce some notation. Now, I found this notation to be confusing the first time I saw it as a student. So don't get intimidated by the notation. It's really a very simple idea. So let's say that the amount of explaining that is done by a model with just one of these x's in it is SSR. So SSR is how much is explained by a model with just x sub j in it. SSE sub x sub j is going to be what is unexplained by a model with just that variable in it. Then if I add these commas, okay, so this will be what is explained by both predictors. This is what is left unexplained by both predictors. With these terms defined, we can now think about the extra sum of squares. So the extra sum of squares simply tell us how much additional explaining do we do if we bring x2 into a model that already has x1 in it. So the way this is going to be defined is we're going to take the total explaining done by both predictors and subtract off what would be done with x1 alone. And so the difference then is going to tell us the additional explaining done by bringing x2 into that model. So that's all an extra sum of squares is. These go by a number of names. So type 1 sums of squares in SAS and SPSS, sequential sums of squares in Minitab, and let's go to an example. If we return to the click ballpoint pens example, I've run a couple of models. So this first model is if you regress sales on advertising alone. The second model is if you regress sales on the representatives alone. And then this third model is going to be the combined ones. And I've also printed the ANOVA tables for those three models. So let's just walk through the extra sum of squares. So let's consider the extra sum of squares for bringing reps into a model that already has ads in it. All right, well, the amount of explaining done by ads alone is 63,451, and that number comes from right here. So that's what we would explain with adds alone. Now, the amount of explaining that we do with both is 52778. So we can call that SSR adds and reps 52778. So then what do we get by bringing reps into a model that already has adds in it? Well, it's simply the difference between those two numbers. So 52778 less what you'd get with adds alone. So the additional explaining done by reps is about 59,000. Now likewise, we could do the same if we wanted to know what do you get by bringing adds into a model that already has reps in it. Well, just take the difference. So 52778 minus what you'd get with reps alone, which is going to come from this ANOVA table. And so you'll see that adds will bring an additional 57,617 of explaining. Now you can get these extra sums of squares in R with the ANOVA command. So you'll see I've estimated a model first with adds, then I bring reps, and so when you type ANOVA, you'll see that okay, adds do 46,451, which is what we saw up there, and then you get an additional 59 if you bring reps in, and then you have errors of 75,000. Now where's that number coming from? Well, that number is what is left over from this model with both variables in it. Now if you remember, what is explained by the model plus what is unexplained is the total. So the total variation in this model is 598, and that's true across all three of these models. We're just breaking up this 598 in different ways. Sometimes you'll see this written as a bar chart. So let me show you a little bar chart that I made. And so I've got a little. So this first column is going to be the explaining done by adds. Then if you add reps to that, here's what's unexplained by that. The second column will be here's what you get if you bring reps in. If you add adds to reps, then here's the total. So you see that those numbers match up exactly what we had on this slide. Now you can create a bar chart, and this bar chart, the numbers are so close to each other, they look identical, but they're not. This bar is the explaining done by adds. If you bring reps in, this is the additional explaining. That top slice is the error. So the total height of the bar is SST, and then this other bar is what happens if you bring reps in first, then adds, and here's the error that's left over. Those two slices are exactly equal. These two slices are going to be slightly different. So this one has a size of 59,000, this one is 57,000 something. It's just that because the scale is so big, they look identical. So those are the extra sums of squares. A very closely related topic is partial sums of squares, also known as type 3 sums of squares in programs like SAS and others. So what is a partial sum of squares? So partial sums of squares answer a very simple question. How much do I lose if I drop a variable from the model? So think about dropping one term, what do you lose? So let's go back to this model that I estimated on the click ballpoint pens example. If I do a drop 1 on it, okay, then I get the following two terms. And these two numbers should look very familiar to you. So this line is saying if I were to drop adds, I lose about 57,600. If I were to drop reps, I lose about 59,327. And so those numbers are really just these extra sum of squares from the previous slide. So if adds is the last thing in, it adds 59. Likewise, if you drop adds, sorry, I think we got that one wrong. If we add reps, if reps is the last thing in, you add about 59, or equivalently, if you drop reps, you lose 59. Okay, if we go back here, if adds is the last thing in, you get about 57,617. Likewise, if you were to drop adds, you lose 57,617. All right, so these concepts are going to be very useful to us. To get the partial sums of squares, we use drop 1. To get the extra sums of squares, which build this up incrementally, we use ANOVA. And here's a slightly more complicated example that really highlights the difference between the two types of sums of squares. So if I build the model x1 plus x2 plus x3, extra sums of squares are going to tell you, first off, what do you get by bringing x1 in? Now if you already have x1 in, what do you get by adding x2? And then if you already have x1 and x2 in, what do you get by having x3? The partial sums of squares simply tell you if you got rid of any one of these terms, what would you lose? Now we can use these in doing simple tests of hypotheses and more complicated ones, including the overall test of significance that we've talked about earlier. So if you want to test whether a single beta is significant, all we're going to do is look at the extra sums of squares or the partial sums of squares for that term. So those two are going to be equivalent. So what do you lose by dropping x1, given that the other variables are retained? We'll divide that by 1 since there's only one parameter. I will divide that by the mean squared error. This has an F distribution. Sometimes we may want to look at multiple betas. In that case, the test is the same. What do we gain by adding those two variables to the model, or equivalently, what do you lose by dropping them? Now, since there's two terms, we're going to divide by 2 and then divide by the same mean squared error. And so this is sometimes called the partial F test. In my next video, we'll work through an example where I show you how to use these F tests.